Okay, hey folks, let's keep it going. We are now going to solve the tunneling problem. We've set up the Schrodinger equations, but now we have to apply the boundary conditions to actually solve it. So be familiar with how to solve the tunneling problem with 4 equations and 6 unknowns. Oh my God, how are we going to do that? Stay tuned and find out. Okay, so this is where we ended up last time. We set up our general solution to the Schrodinger equation for all 3 regions. Recall in regions 1 and 3, we got imaginary solutions, which correspond to oscillating wave functions corresponding to sines and cosines. And in region 2, we got real solutions corresponding to some exponential decay or growth analogous to classical dampening. We also have our respective wave number solutions, which for region 1 and 3 are the same, albeit region 3 has a reduced energy compared to region 1. And in region 2, our wave number solution includes this potential energy term. So now if we look here right at the boundary and the zoom in that we can see right here, we should note that we're going to have some very specific conditions to meet to solve this according to the boundary conditions. And those conditions are the following. The wave functions must be continuous at the edges of the barrier, and their slopes also must be continuous at those same positions. So we're going to have to set up some algebraic expressions to account for that. So hopefully I have left enough room. Let's go for it. So first, the wave functions have to be continuous. So really the value of the wave function at the border of region 2 and region 1 have to be the same, and the value of the wave function at the boundary of region 2 and 3 have to be the same. And so for convenience, we're going to call this boundary right there x equals 0, and we're going to call this boundary right there x equals L. So for that first region, for that first condition, we need to set region 1 equal to region 2. So we can say AEIKX plus BE negative IKX equals CE kappa X plus DE negative kappa X. And we can make a very simple adjustment to this by noting that x equals 0 at that boundary. And thus we can see we have all of these are exponentials raised to the x power. So e to the 0 power equals 1. So this is going to reduce quite simply into a plus b equals c plus d. Okay, beautiful. There is our first condition. Now, similarly, we know the value of the wave function at region 2 has to equal the value of the wave function at region 3. So let's set that up. So we can say now that is CE kappa X plus DE negative kappa X equals A prime E IKX plus B prime E negative IKX. And because at this condition x equals L, we can't quite simplify this as much as we want to. So I'm just going to replace x with L, and we'll note that that is our second equation here. So CE kappa L plus DE negative kappa L must equal A prime E IKL plus B prime E negative IKL. And so I'll start highlighting these here. So this was our first equation. This was our second equation. And now we can generate 2 more equations under the second principle that the slopes must be continuous at the boundary of our wave function. So what that means now is we have to take the derivatives of each of these wave functions and set them equal to each other and apply the appropriate condition. So I'm taking the derivative of this first wave function. I'm going to get A I K E I K X, that's a mouthful, plus, and oops, that was a negative because, right, we've got a negative in the exponential, right, taking the derivative of this term. So that's negative B I K E negative I K X. Lovely. So now we want to take the derivative of region 2. So that is going to be, let's see, C kappa E kappa X minus D kappa E negative kappa X. All right, and so just like we did before, we know at that boundary that X equals 0 and E raised to the 0 power equals 1. So we can make another simplification like we did before. And what we will end up with is A I K minus B I K equals C kappa minus D kappa. And there is our third equation. Let's go ahead and highlight that. Okay, beautiful. And now, as you might guess, for our fourth equation, we're going to set the derivatives of region 2 and region 3 equal to each other and plug in our boundary condition. So we already got the derivative for region 2 right there. We can just copy that over. So that was C kappa E kappa X minus D kappa E negative kappa X. And that all equals the derivative of region 3. So that's going to go as A prime I K E I K X minus B prime E. Oops, I skipped the I's and the K's. Let's make sure that we've got that correctly. So, oh, excuse me, I'm not going to edit that out. Okay, negative B prime I K E negative I K X. Just checking that I didn't lose my place. Okay, beautiful. And then we've got to plug in X equals L into that, so we can't simplify that, but let's just write it down for completion. So that's C kappa E kappa L minus D kappa E negative kappa L equals A prime I K E I K L minus B prime I K E negative I K L. And we'll highlight it to note that here are our 4 equations. And if you count it up, we've got 6 unknowns. So let's check that out. So here are all of those written out again, much easier to read besides my crappy handwriting. And our 6 unknowns are A, B, C, D, A prime, B prime. And now, as we might start to guess, we can't do this, right? We need, for 6 unknowns, 6 equations, okay? But we can start to think about this problem logically and see if there's anything that we can eliminate. So in this problem, we have set this up such that overall, we are interested in particles moving from left all the way right, okay? So we note in region 1, we will have left moving particles, but we also get right moving particles, right? The reflecting off of the barrier. In region 2, we also have left moving particles, but we also get some reflected particles coming off the barrier. And then finally, in our region 3, we only have left moving particles because we haven't put any kind of barrier right there. We're just letting those particles fly all the way through. So as we might guess, we can ascribe these constants to those different motions. So for example, in region 1, we can call the left moving particles A and the right moving particles B. Within region 2, we can call the right moving particles C. I feel like I've been saying this backwards, but I hope that you get the idea. We can call the right moving particles C and the left moving particles D. Up here, the right moving particles are A and the left moving particles are B. Apologies for that confusion. And then finally, in region 3, our right moving particles are A prime, and because we haven't put a barrier for the particles to reflect off of, we can throw out that B prime term for this particular problem. So now we're down to 5 unknowns with 4 equations. So we either need to get rid of one of those unknowns somehow or add an additional equation. Well, as it turns out, we can add a 5th equation, and that has to do with the transmission probability. Okay, so let's write that down. Transmission probability, and that is based on the amplitudes of region 3 over region 1. So in other words, we can call the transmission probability some constant t, which must be less than or equal to 1, where the 1 corresponds to 100%, right? So that gives us some kind of boundary condition for the transmission probability. And additionally, we can also say the transmission probability is related to the amplitudes of region 3 over region 1. So in other words, we can say the A prime square modulus over the A square modulus is going to give us that transmission probability. So that creates a 5th equation with a 5th unknown. And then, of course, now we still have to have some kind of equation or some kind of way to calculate t. We can't just assume that it's based on these things, right? It is based on these things, rather, but the way that I've put this together, it's a circular argument. So we do have to have another way of coming up with an equation for t. And by plugging in these expressions for the square modulus of A prime and A squared, the square modulus of A, we can get that equation. And I'm not going to go through that algebra, but it is able to be done. It's not overly complicated. And I'll talk about that in the next video.